Good evening, everyone. I'm Nandakumar Jia from Cybersecurity Department. Today, I will be presenting our Phase 1 research work titled Personal Silence Zone. So, this work focuses on the design and simulation based validation of a localized active noise control system intended to improve the acoustic comfort in open and shared environments. The goal of this presentation is to explain the motivation behind the problem, the proposed system, the methodology used, and finally demonstrate a simulation based demo that validates the feasibility of our approach. So, the noise pollution has become an unavoidable problem in modern life, especially in urban and shared environments such as offices, libraries, hostels, and homes. Common noises such as traffic sounds, air conditioners surroundings, and not suitable for prolonged and shared usage. The passive soundproofing methods require structural modifications, and so they are very costly and are often ineffective for low frequency noise. Because of those limitations, there is a need of non-intrusive and localized solution that can reduce the noise user without physical enclosures or wearable device. This need forms the core motivation behind our research. So why active noise control ANC? Active noise control is particularly effective for low frequency noise while passive methods fail. ANC works on the principle of destructive interference where an anti-noise signal of opposite phase is generated to cancel the unwanted noise. When AIS is successfully implemented in headphones and enclosed systems, extending it to open environment is still a challenging research problem. So work explores the challenge by proposing a personal silence zone, which focus on creating a quiet region around the user rather than isolating the user entirely. So the objective and research contribution, the primary objective of this research is to design an evaluate system capable of creating a localized silence zone using active noise control techniques. So the key contribution of this phase 1 research includes a modular system designs for localized noise control and applications of adaptive ANC algorithm, simulation-based validations to study the feasibility and performance. This work serves as a foundation for future real-time hardware implementation. So our related methodology, this noise detections, microphones are placed strategically around the user to capture the ambient environment noise. These microphones continuously sense and surrounds the pressure variations and convert them into electrical signature for further processing. This focusing is on capturing the dominant low frequency noise components such as traffic hum, fan noise, and air conditioner sounds. And the signal processing. The captured noise signals are processed using digital signal processing DSP techniques. Noise signals are analyzed in both time and frequency domains using filtering and fast Fourier transform methods to identify the dominant noise frequencies that need to be cancelled. In system identification, an adaptive system identification technique is used to model the primary path and the secondary path. Accurate modeling of these paths is essential for stable and effective ANC performance, especially in open environments. Active noise control, we already saw that active noise control is the key thing which able to process the things which has been modeled to it. Then a zone creation. So this is positioned to form a localized silence zone around the user. In embedded system integration, the entire ANC system is implemented on an embedded controller. Microcontroller, the controller manages the real-time signal acquisition and processing, the adaptive filtering and synchronization between microphones and speakers. In evaluation and testing, the system is tested using real-world noise sources such as fans, AC units, and traffic noise. Performance is evaluated based on noise reduction level and system latency stability. Optimization. Filter parameters, microphones, and speaker placement and algorithm settings are optimized to improve the noise cancellation. So let's see the diagram system architecture. So this system architecture follows a closed loop control structure consisting of sensing, processing, and actuation stages. First, the microphone captures the noise at the sensing stage. The processing stage applies DSP techniques such as FFT and adaptive filtering. This actuation stage emits an anti-noise through speakers while an error microphone provides feedback. This closed loop design ensures a stable adaptive noise cancellation under changing environment conditions. So these are the use case diagrams, how it works for the user. First uses so that we can see that how he uses some microphones, and this is a UML diagrams like, and for admin page, uh, there will be settings like this, and this is a class diagram how it works, and the sequence diagram that how really it works from the user first sends the noise environment, then it captures the ambient noise, then makes the filtration methods, and then sends reback a clear noise to the user. So these are the diagrams. So now let's see the what are the algorithms used. An LLMS-based adaptive active noise control algorithm is applied. This algorithm continuously adapts its filter coefficient based on the error signal, allowing it to learn the noise characteristics and generate an appropriate anti-noise signal. NLMS is chosen because it offers a stable and faster convergence, especially when the signal power varies and which is common in real-world environments. And the normalized least square. So this is an LMS and then adaptive noise cancellation algorithm used to generate an anti-noise signal with the same amplitude and opposite phase as unwanted noise, resulting in destructive interface within the target zone. Is used to detect an object in the image or videos. Then min-max ANC algorithm used to minimize the maximize residual error within the silence zone. This algorithm is effective for controlling the noise across a spatial region rather than a signal point and make it suitable for creating a localized quiet zone. The system identification algorithm used to model the primary path and secondary path in the acoustic environment. Adaptive filter estimates impulse response to ensure accurate phase alignment for noise cancellation. And then the fast Fourier transform (FFT) algorithm transforms the time domain noise signals into frequency domain to identify dominant low frequency components targeted for cancellation. The digital filtering algorithms includes low pass and band pass filters to isolate noise frequencies relevant for ANC while reducing unwanted high frequency components. Error signal minimization algorithm continuously monitors the residual noise using error microphones and adjusts the control signals to minimize the sound pressure levels in real time. An adaptive parameter tuning the algorithm automatically adjusts filter step size and again parameters to maintain stability under changing environment conditions. So the hardware and software selections we made for our project, the sensors like condenser microphones or reference microphones or error microphone. Then the actuators is a full range speakers or power amplitude module. Then the main processing unit is IoT enabled microcontroller or any DSP board. Then communication modules such as Wi-Fi and Bluetooth module. Then IoT platform is like ThinkSpeak, Blink or Firebase. So here the real implementation that how it works means this project is implemented using embedded C based on signal processing within the real-time audio handling. The system includes the software modules that continuously acquire environment noise signals through microphones. And the ANC algorithms like NLMS and MinMax are implemented on IoT embedded microcontroller to generate an anti-noise signals in real time. So that the noise the audio can be filtered within this. The processed anti-noise signal is sent to speakers which generate sound waves of opposite phase to cancel and detect the noises. The system categorizes the noises based on the implementations and the frequency bands noise updations to it to maintain the effective cancellation. The output is observed as a reduction in the sound pressure level dB within the defined personal silence zone. And system perform matrices such as ambient noise level, residual noise level, and latency as monitored and optionally uploaded for an IoT platform. So now let's I need to explain the code. Like I'm using a demo video for it, how it works on that. So just wait a minute, I will show it. So yeah, here is a demo video setup for the phase 1. The simulation is executed in Python environment using Google Colab. We simulate low frequency environment noise similar to fan and traffic sounds by combining a sinusoidal signal with random noise. So first, it's a graph time domain analysis. So this plot that ambient noise signal with the signal after applying ANC. We can clearly observe a reduction in amplitude indicating effective suppression. Then second is a learning curve. So this learning curve shows the reduction in squared area over iterations. This confirms that the stable convergence for real-time feasibility. Then the graph 3 that represents a noise power comparison. This bar graph provides a clear quantitative comparison of noise power before and after ANC, further validating systems and performance. So overall, the simulation results demonstrate that the proposed methodology effectively reduces the low frequency environment noise and supports the feasibility for creating a localized silent zone without physical isolation. So these are the code which explains how it works, and these are the output. So I've already seen on that. So as a result, we can able to drastically reduce the noises in the audio. So the conclusion is noise pollution remains a major challenge affecting comfort, health, and productivity. Existing solutions like headphones, passive panels, and soundproofing have significant limitations. But the personal silence zone provides a localized, non-intrusive, and cost-effective solutions using active noise control ANC. This system effectively minimizes low-frequency environment noises without isolating the user. So this project contributes towards the development of next generation smart acoustic solutions for everyday environments. So mainly our future work is that we have been shown that the real-time hardware environment is a future work, and multi-user silent zone generations and machine learning based adaptive filters and integration with smart environment. These are the future works we need to done in our phase 2 project. This is for phase 1. We just researched about how it works and how it performs in a real-time things, and also we have been developed simulations that have been done in a Google Colab. So these are the reference, and the one thing is this work is positioned to a project phase 1 research, studying focusing on design and simulation based validations with real-time implementation plan for the future work. So thank you for the opportunity.